Hello students, welcome to yet another video on mathematical logic. We already have started lecture series on mathematical logic and other topic from our textbooks. So if you are interested to see similar videos like a trigonometric differential equation, another topic like matrix determinant plus a pair of straight line, another binomial and other topics, if you are interested to learn, do check out in my playlist. I already uploaded plenty of the videos on my channel. Okay, so if you are interested to see more videos similar like this, let me know in a comment section what you found difficult in mathematics. I will come up with the similar videos like my previous one. Okay, so in my today's video I'm gonna explain to you all mathematical logic, basic concept based on mathematical logic, and plus after that we'll go for the some of the previous year board questions. Okay, so let's get start our today's lecture. So we'll go for basic concept first of all, and then we'll move for the detailed understanding of our previous year questions. Okay, now mathematical logic, what we learn in our mathematical logic. So complete lecture already uploaded in my channel, so if you wanted to see, do check it out. Okay, but in mathematical logic we generally operate on mathematical statements. Okay, so whether their statement truth value it is a true or whether their truth value is a false. Okay, so truth value of a statement, we start mathematical logic from the truth value of a statement. Subsequently we have there some connectors in our statements. Okay, so first what we have here, truth value of a statement. Truth value of statement. Okay, first what we learn, truth value of a statement, that means statement whether it is a true or whether it is a false. Okay, so it comes falls under truth value of a statement. After the truth value of a statement we comes under the connectors of statements. Like a connectors means as we in our daily life we use connectors like and, or, again not, if, then, if and only if. These type of the connectors also helpful in our mathematics. Okay, but mathematics is having mathematics subject having its own language. So to define that own language, this connector we taken with a different name. Like and word we taken conjunction. Okay, or word we have taken like a disjunction. Okay, the single implies we have taken implication or conditional. Double implication we have taken double implies we have taken double implication or biconditional. Or not word also we have taken as a negation. Okay, so we have 4 to 5 types of the connector that we are going to use in our subsequent part of lecture. Okay, so first is a and, second or, second connector we have or here, second connector is a or. Okay, third connector is a if and only if. Okay, if and only. Fourth connector is here if, then. Okay, fourth connector here it is if and if, then, and fifth connector it is here negation. Okay, that means not. Okay, these are the regular life connectors that we use while we are speaking English. Okay, we use our this word we use in our English. Okay, but in mathematics it is having its own language, so we convert that and as a conjunction or as a disjunction, if and only if as a biconditional, if then as a conditional, and not as a negation. Okay, so using all these value we will define our further examples and subsequent part. Okay, so these are the connector parts of our examples. Okay, so after the connector parts we fall under the truth value of a statement. Okay, so whether if we take two different statement, if we take a two different statement like a P and Q, okay, we have to take the possible truth value for these statements. Okay, so if I consider one single statement P, so we can say that whether that statement is a true or whether that statement is a false. Okay, that means it falls under only the two possible truth values. Okay, whether it is a true or whether it is a false. Okay, but what happen if we take a two statement together? Okay, so if we take a two statement together like a P and Q, so how can we define the truth value for two statement together? Okay, So first, whether first statement is a true or false, second statement is a true or false. Okay, that means we have to take the probable chances for these two statement together. Okay, so now let me see, let me explain you how can we write the truth value for a two statement P and Q. Okay, so here I consider statement P as a true. Okay, if first statement is a true, then second it goes the true. Okay, that means we can take first statement true, second as well as true. Okay, if first statement goes true, then we can write second statement is a false. Okay, if first statement if I taken false, then second statement it goes to the true. Okay, if I taken first statement false, second statement we can also take it as the false. Okay, so these are the possible value for defining our statement pattern, whether it is a true or whether it is a false. Okay, so it falls under these four possible chances. Okay, so this is only for the two statement. Okay, so subsequent part, if we get the three statement together, okay, so their probable chances goes as the 8. Okay, that means first four statement we have to take true, second four statement we have to take false, and then P, Q, R we have to define it there. Okay, so I will explain that part in our subsequent examples. Okay, because these examples are going to be the next part of our previous year examples. Okay, so I'm expecting that you all have understood the truth values for our statement. Okay, now next part, after the truth value for our statement, we have converse, inverse, contrapositive. Okay, so this maybe consider this one as a recap for our complete lecture series. Okay, because as board exam is coming closer, I'm expecting that you all need to understand only the basic concept here. That's why I'm taking these recap videos. Okay, so if you are interested to see full videos, request me in my comment section. Okay, we'll go for that one also. Already we have uploaded the complete full lectures series. Okay, so you may check it out in my playlist. Okay, okay, now after that truth value, what I have explained, the statement pattern, how can we define converse, inverse and contrapositive for the statement. Okay, so converse, inverse, contrapositive. Now consider that if I'm having the statement pattern statement as a P implies Q. Okay, if I have statement if P then Q. Okay, P and Q consider as the two different statement. Okay, P and Q consider two different statement, and if they are having connection between them, if and then, so we write if statement is a P implies a Q, then how we write it's a converse, inverse and contrapositive. Okay, so for converse statement pattern, if you have P implies Q, then we write it's a converse as negation P implies negation Q. Okay, if statement pattern is a P implies Q, then converse we write converse means we have to take the written part from the next statement to first statement. Okay, so converse we write a Q implies P. Okay, so if we have statement P implies Q, then its converse goes to the Q implies P, then inverse goes to, it's the inverse of this statement, we write negation of a P implies negation of a Q. Negation of P implies negation of Q means not P then not Q. Okay, so if statement pattern not true, then there it implies that its implication also not true. Okay, this is the part of inverse, and the contrapositive, it goes to the negation of the converse. Okay, so for contrapositive statement, we write a negation of a Q implies negation of P. Okay, so these are the statement here. P implies Q, its inverse defined as negation of P implies negation of Q, its a converse defined as Q implies P, and the contrapositive as a negation of Q implies negation of P. Okay, so P and Q, it represent here two different statement. You all need to understand this one. Okay, so all I have explained everything. Okay, if you wanted to see, do check it out. Okay, in my I button. Okay, you can see their videos. Okay, I hope you all have understood the converse, inverse, contrapositive pattern for our statement. Then after that we have logic gates. Okay, logic gates, it represent that whether circuit currents flows or not. Okay, so that means when we have, and how can we define the logic gate, when we have, or how can we define when we have negation, that means when circuit is closed or circuit is open, that time we define negation. So we are going to understand everything in a detail as a subsequent part of our board exam. Okay, and plus one more thing here, that these examples, okay, are having truth table too. Okay, that means if we plot the if we write the logical statement from our truth table, from our given data, so we have to simplify that into the form of a truth table. Okay, but in the form of a truth table, we don't have the truth value as a true and false. Instead of a true and false, we are taking 1 and 0 as their truth values. Okay, I'm expecting that you all have understood this part. Okay, let's move for the next part here. So this is the part from the previous year board exam question paper. Okay, so our first question I have taken from the board exam question paper, which is the latest question from the March 2023 board exam. Okay, ask for 4 marks in our March 2023 board exam. Okay, so 4 marks question, it is this one. So we have to simplify the given circuit by writing its logical expressions. Okay, so first of all, what we do, first of all we have to write the logical expression from this circuit and also write the conclusion. At the end we have to define the conclusion from our circuit. Okay, so first of all, define the logical circuit, define the logical, by using logical circuit, define the logical expression. Okay, that means we have to convert our logical circuit in the form of a logical expression, whether it should be the current flows in lamp or not. Okay, now see that how many switches we have here, S1, S1 dash, S2 dash and S2. Okay, now first of all, whenever such examples coming in your board exam, what you all need to do, first of all define their circuit switches. Okay, so first task is here to define the switches from our logical circuit. Okay, so once you come to understand the switches, okay, switches from our logical circuit, a subsequent part you can define it using logical expression. Okay, now see that how many switches we do have, 4 number of switches, and S1 and S1 dash, you need to understand the difference between these two words. Okay, because these two words carries 1 or 2 marks in your board exam, so that's why you all have to mention that part in our paper. Okay, so let me explain the difference between S1 and S1 dash. Okay, S1 and S1 dash, we want the difference between S1 and S1 dash. Okay, now see that if S1 is a statement, if S1 is a statement from our logical expression, then S1 dash gives us the negation of our given statement. What it gives? Negation of our given statement. That means dash represent negation from our statement. Okay, now let's define first of all the values from our logical expression, that is the values of our switches. Okay, so first switch we have here, total number of switches we have 4. Okay, so we have to define all these switches first, then find out the required answer. Okay, so what we have, S1 here, and S1 it represent switch, okay, S1 which represents switch. Okay, so S1 is a switch, whether it is a open or close, will define as using the diagram. Okay, so consider that first S1 is a switch as a some statement like a P, Q, R. Okay, so I consider statement P as a switch, switch S1 is closed. Okay, switch S1 is a closed. Okay, and S1 dash, it represents whether switch S1 is a closed or open. Okay, so we dash means we don't have any confirmation about the switch is closed or open, so we consider it as the whether switch is closed or open. Take this condition together for different switches. Okay, so in next part we take as a statement Q. Okay, so P is a switch S1 closed. After that we have again next switch Q. Okay, we have next switch which is a Q, so we represent switch S2 is closed. That means whenever we have switch closed, only then we can say current flowing from our circuit, and when we have switch open, that may be flow or may be don't. Okay, so it is depend on the figure. So if we have parallel connection or series connection, so it is completely based current flow on their switches. Okay, so we have switch S1 is a closed as a statement P, switch S2 is a closed as a statement Q. Okay, so we do have two statement. Now let's define for S1 dash and S2 dash. Okay, so S1 dash. Okay, so next S1 dash is defined as switch S1 is a closed or may be open. Okay, switch S1 is a closed or may be open. Okay, switch S1 is a closed or maybe it is open. Okay, so similarly for S2 dash, but what we have here, S1 and S2 both represent the statement P and Q. Okay, so you all have to mention that switch S1 what it represent and what the switch S2 represent. Okay, so S2 dash it written as switch S2 is closed or maybe it open. Okay, switch S2 is a closed. Okay, switch S2 is a closed or may be it open. Okay, so we cannot confirm the condition here for the negation, so that's why we have to consider both of the cases together. Okay, so we have switch S1 dash and S2 dash I define over here, and switch P and Q define here. Okay, now let's take all these condition together and write the logical expression using these switches. Okay, now see that whenever we have parallel switches, we go for the AND. Okay, and when we have series switches or parallel switches, okay, when we have series switches, that means we need both of the switches there on. Okay, so that's why we are taking AND. That means both statement need to be working at the same time. Okay, only that time that AND statement can be defined, and only then our circuit has a flowing current. Okay, now see that we have only the parallel switches here, and after that series switches it comes for this complete parallel switches, and at the end we have again series switches. Okay, now let's write their value using our defined the variable. Okay, so I consider S1 as a P, and S2 as a Q. Okay, so S1 dash means it's the opposite, that means negation of P, and S2 dash it is a negation of Q. Now let's define these values in our circuit. So S1, we have first statement S1, and S1 represents switch is closed. Okay, so S1 represents switch is a closed and denoted as a P. Okay, so I define S1 as a P. Okay, which is a closed circuit. So after this, now we can see here we have after S1 series switches. Okay, and whenever we have series switches, we take it AND. Okay, AND means conjunction. Okay, already we have learned about the conjunction. So in mathematical language, AND represent it is as a conjunction. Okay, so already as earlier I have explained all of them. So let's move for the next. We have first S1, after that series switch. Okay, with a S1 dash and S2 dash. Now S1 dash, which represent series S1 is a closed or open. Okay, now if S1 is a P, okay, let me explain it here it separately. If S1 which is equal to P, this implies S1 dash represent negation of a P. Okay, so meaning for that dash, it is a negation, that means completely negative meaning from our statement. Okay, so that's why we have taken S1 dash as a negation P. So similarly do it for the S2 dash. So what it comes for the S2 dash gives us the value negation of Q. Okay, so what is the value for S2 dash? which gives us the negation Q. Now substitute all this value, revert them back into our example, so you will get the required answer. So now see that S1 dash and S2 dash, these are the parallel connection, and whenever in our logic gates we have parallel connection, we take OR between them. Okay, so we have S1 and, that means P and S2 S1 dash or S2 dash. So S1 dash we have negation of P, or means we have here both the connection which is in the parallel form. Why we are taking OR here? Because whenever current started flowing from this point, so it goes to the up. If upper circuit it is on or upper switch is on, so currently obviously current can flow, because these are the series parallel switches. Okay, so if one switch is off, it's not necessary that the another switch may be off or may be on. Okay, so if one switch is off, maybe another switch is on. Okay, so when current not going to flow from there, so that in the condition that both of the switches are completely off. Okay, so then we say that current cannot flow from there. But we have the two parallel switches. In such a case, we cannot predict the value here, so current can flow from here as well from the downside. Okay, so this is the way we can define OR switch. So P and negation of P, or after that you can see S2 dash here. S2 dash it represents negation of Q. Okay, P and negation of P or negation of Q. Now see that after that we have for these two connection again parallel series connection for S2. Okay, so series connection for S2 it takes as a AND value. Okay, and S2 it represented as the switch. S2 is a close which represented as the Q. Okay, so this is our required answer. Now see that how easy question are coming in our board exam. So our answer, it is coming only in 3 to 4 steps. These types of the examples are quite easy. Okay, so first of all in our exam we have to grab such a question. So only this question helps you to get higher score in our board exam. Okay, attempt this question first, you will get the good marks. Okay, so that question asked for 4 marks in our March 2023 board exam. Okay, so I am expecting that you all have understood the solution. So even after, if you found anything difficult, let me know in comment section. Okay, so now let's move for the next example. Yeah, we have next example. We have to express the following circuit. So we have given circuit here, and we have to express it into the logical form. Okay, or logical expression. Now see that example which asked in board February 2020 board exam. Okay, so it is for the 4 marks. Okay, it is for the 4 marks in our February 2020 board exam. Now see that only answer which is coming in 4 to 5 steps, and these examples gives you 4 marks. So mathematical logic, the chapter mathematical logic, it is a scoring chapter. Okay, so do prepare it well. Okay, so first of all, what we do for this solution? Okay, define their switches first. Okay, define their switches. So we have switch S1, S2 and S3. Okay, so we'll see their parallel and series connection later on. First of all, we represent here the value for S1, S2, S3. Okay, now we don't have any negation or S1 dash, S2 dash, so the current always will be the form of a flowing. Okay, so S1 can be closed, only can be closed. Okay, so we cannot say can be open or closed, it is only the closed circuit. Okay, so represent using the variable S1, S2, S3, and then go for the logical circuit. Okay, so first what we have here, let me change the color. So we have here S1. So S1 is a switch. Okay, so you all have to explain what it is S1, what it is the S2 and S3. Okay, S1 which is a switch. Okay, now represent that switches as some form of a statement. Okay, so I consider here S1 as a P, so P can be written as switch S1. Switch S1 is closed. Why it is closed? Because we don't have negation there. Okay, again let's define the statement Q. Now see that we have S1, S2, S3, three different switches. That means we need to define three different variable for statement variable for these switches. Okay, so switch S1, it is closed, we define as a P. Now for let's go for the switch S2. S2 is A closed. Okay, Q is a switch, S2 is a closed. After that we have S3, consider it is R. Okay, switch S3 is A closed. Switch S3 is a closed. So we have three different statement P, Q, R. Now think about it, about their parallel and series connection. Okay, now we have two parallel connection, S1 between S1 and S2, S3, and the series connection between S2 and S3. So when we have series connection, take and between them, and when we have parallel connection, take or between them. Okay, so there is a logical symbolic form. Okay, write the symbolic form directly. Symbolic form. Okay, symbolic form. Now switch S1 represent the statement P. Okay, started from the beginning. Okay, so S1 start our switching circuit. Okay, so S1 represent P. Okay, S1 represent P. S2 and S3 both are having their conjunction between them, and between S1 and S2, S3 there is a disjunction. Okay, so S1 or Q, S2 represent as a Q, so I consider switch S2 is a closed as a Q. After that and switch S3 is a R. Okay, so this one is a complete switching symbolic form. Okay, now see that how easy the solution it is. Just we have to define their symbolic form from our logical expression. Okay, so S1, S2, S3, three different statement. Two of them are in a series and two of them are in a parallel form. Okay, so parallel form can be defined as or, that means using a disjunction, and series connection it can be defined as conjunction or and. Okay, so I'm expecting that you all have understood this one. So this one is a very easy question which asked in February 2020 board exam. All are the latest question from your board exam. Okay, so which asked for 4 marks. I'm expecting that it's nothing difficult here. So just we need to understand when current can flow from our lamp. Okay, okay, that's it only for our our example. Okay, so let's move for the next example. Okay, so we in our next example find the symbolic form of the given switching circuit. Okay, so first of all we have to find out the symbolic form, then construct switching table and interpret your result. Okay, now see that by using our switching table, okay, switching circuit, okay, so we have to convert that switching circuit first of all in the form of symbolic form. Okay, and once we come to get understand the symbolic form, then convert that symbolic form into the switching table. Okay, into the switching table. So S1, S2, S1 dash, S2 dash, we have only two statement, S1, S2. So consider that first statement as a S1, second statement as a S2. S1 dash, it is the negation of first statement, S2 as a negation of a second statement. Okay, now let's define that statement first. Okay, so now see here, so we have symbolic form. Let me change the color. So now see here, we have two statement and two negation of them. Okay, so consider yes is switches as a yes. Okay, switches as yes, consider switches as a yes. Okay, then S1. So now let's represent what is mean by S1. Okay, so consider it is as the some different statement. It is not that necessary you have to consider PQR only. You may go for LM, EN, anything can be possible. This is just arbitrary variable. Okay, that you can consider it here. So consider statement P for our switch S1. Okay, so statement P, it represent switch S1 is closed. Okay, switch S1 is closed. Very good. Now let's go for the next statement, Q. So what Q represent here? Switch S2 is closed. Okay, so you all have to define the value for P and Q before you go for your solution. Okay, yes, P, Q. Let's go for the S1 dash. S1 dash represents switch S1 may be closed or may be open. Okay, so we cannot guarantee for its negation. So that's why we have to take negation as may be open or close. Okay, sometimes we have to predict the values in our mathematical logic chapter. Okay, so it is completely based on the part of a logic. So maybe we have to predict sometimes. Okay, so S1 dash. Okay, so it represents S1 dash as a switch, whether switch it is a closed or open. Okay, switch is closed or open, or we represent S1 dash as a negation of P. Okay, and similarly do it for S2 dash. Okay, switch S2, switch is closed or open. Okay, it must to write this explanatory part in your board exam. Okay, so don't forget to write this one, because this part carries 1 or 2 marks. Okay, so S2 dash represents switch, yes, switch closed or open. Okay, switch, let me write it again, switch closed or open, switch closed or open. Okay, okay, switch closed or open here. Okay, yes, for S2 dash, and it represented as a negation of a Q. Okay, now apply all of these condition to our logic circuit diagram. Okay, and convert it into the symbolic form. Now let's see what is the symbolic form coming. Now we don't have only the solution, these 4 steps, because we have to construct this logical circuit table. Okay, that whether it represent whether the current flows or not from our circuit. Okay, using our logical circuit. Okay, so what we get here, switching circuit, symbolic form of a switching circuit. Okay, symbolic form. You all have to explain all of these steps. Okay, so symbolic form. So represent the symbolic form using our circuit. Okay, S1 and S2 both are in a parallel condition. So P and Q. Okay, parallel means, sorry, P or Q it is coming. Okay, not a and, P or Q it is coming. Yes, between S1 and S2 we have parallel connection, and parallel connection always represent OR, because OR can be used for whether one is true or whether another is false. Okay, that means we have to use OR sign here for the 2 different switches, whether first it is on. Now see that if first switch is on, then lamp can be blown here. Okay, and if second switch is on, first is off, then also light can be blown. Okay, so switch can be current can be flow only when one of the switch is on. Okay, yes, let's move for the first part. Next part, so we have here between these 2 switches as a or sign, and after this we have all are the series switches. Okay, series switches can be represented as and S1 dash. S1 dash, it is a negation of P. Okay, and S2 dash, between them we have negation of a Q. Okay, P or Q and negation of P and negation of Q. Now see that how easy symbolic form it is. Okay, only we have to understand the parallel connection and the series connection for our logical circuit. Okay, so this one is our required symbolic form, but we don't have to stop here. Okay, our next part of the question, it says that construct its a switching table. Okay, construct its a switching table. That means we have to find out the switching table, whether truth value of that tables gives that circuit on or off, okay, and that we have to represent it at the end. Okay, now let's find out the truth table for the switching table. Okay, now see that we have the two statement P and Q. Okay, now for switching table, we take a truth value T as a 1 and a false as a 0. Okay, those are the falsy values we are taking under 0. Okay, like a binary system 1 0. Okay, so false value goes for the 0, true values goes for the 1. Okay, and one more thing I have to mention here, this part from the logic circuit or mathematical logic mostly used in a binary system. Okay, so binary system which is helpful for finding the languages, okay, from our computing. So this is the mathematical logic and or NAND, not NOR, all these circuits are there in our programming language. Okay, so mathematical logic completely based on the programming language. Okay, so this binary system which is coming from this table also. Okay, so that's it only here. Now let's move for the next part. We have to describe here as the switching table. Okay, now we have two statement P and Q. Okay, so till the moment we learn for writing a statement P and Q, their truth value as a T and their truth value as a false. Okay, now instead of a truth value TF, we replace their TF as a 1 and 0. Okay, that means first circuit is having a value 1, that means circuit on, second circuit it is off, another circuit is on, second circuit is off. Okay, so let's go for as per the series connection. Okay, we don't have to take a randomly value, we have to consider the value as per the switching table. Okay, first circuit it is on, another circuit it is in second condition it is on, next it is off, another it is off. Okay, first on, second off, first on, second on, keep first second on at the first time. Okay, so we have to consider the first on, second switch on, first on, second switch off, first off, second switch on, and first off, second switch off. Okay, these all are the possible values for our truth table. Now see that instead of a true, I have taken 1 as the truth value. Okay, and instead of a 0, I have taken 0 as the, instead of a false, I have taken 0 as a false value. Okay, now we want the P or Q. Okay, P or Q, that means P disjunction Q, and P disjunction Q, it says that when we have two false value, it gives only the false. Okay, that means when we have two 0, it gives only the 0, and remaining all are the true, that means remaining all are the 1. Okay, this one is the P or Q. So consider this one is the first statement. Okay, let's go for the negation P and negation Q, because we want the and between or conjunction between of them. So negation of a P, that means all are the opposite values from P. Okay, so which is a 0 0 1 1. Okay, again negation of a Q, 0 1 0 1. Okay, 0 1 0 1. Okay, so negation of P and negation of Q. Now between of these two statement we have and, so negation of P and negation of Q. Okay, so between of these two statement we have and sign here. Now take the and here, so and represent that whenever we have two statement are true. Okay, that means whenever two statements gives the value 1 and 1, okay, that means current flows from the two statement at the same time, then and only then circuit is on here. Okay, now search the two same value 1 1 1 here. Okay, yes, after that we don't have two of this statement one at a same time. Okay, so take all of them 0 then. Okay, so I got the statement phi, first statement and second statement here. Okay, and between these two statement we have and sign. Okay, take the and sign between 1 and 2. Okay, I don't have a space here, I'm taking it downside. So 1 and 2, between 1 and 2 we have to use and that means conjunction here. Okay, so conjunction represent that whenever we have two statement which is a true, okay, that means whenever we have two statement which is a 1, okay, then it goes to the 1. Okay, now see that first statement, second statement, third statement, fourth statement, both of the statement represent here both the circuit do not have one value or true value at the same time. Okay, now in such a case, take all of these values are falsy. Okay, 0 0 0 0. Okay, all these values are falsy. Now we can say that if all values of the circuits it represent 0, that means the falsy value, that means our switching circuit it is off, or it is not currently flowing the current. Okay, so switching circuit off. Okay, we have switching circuit is off. Okay, I'm expecting that you all have understood this solution. Just this table, it is very much important, that can define whether our circuit it is on or off. Okay, so do it carefully. Okay, so that question asked in March 2019 for 4 marks. Okay, so see that how easy questions are coming. Okay, so let's move for the next question. So now next question we have construct the switching circuit for the statement. Okay, so we have given statement. So what we have done in our previous part, we converted our logical circuit into the symbolic form. Okay, now in this situation we have to go for the inverse part. Okay, so we have to go for the inverse part for our statement. Okay, so converse part of a statement, and converse part of a statement it says that go from the domain to reverse image. Okay, so here we have construct the switching circuit from our statement P and Q. Okay, now observe our statement P, Q, negation P, negation Q, between them as a conjunction, disjunction and implication, all you need to understand first. Okay, so now see that first of all represent what the statement P says, what the statement Q says, what for the negation P and negation Q. Okay, so question asked in March 2017 for 4 marks. Okay, so easy question this one. Okay, don't have anything there, just need to replace the values and need to plot the statement. Okay, now we don't have connected question here, so we have to stop after finding their logical circuit. Okay, now represent the values for P and Q. So statement P represent, okay, statement P represent that switch S1 is closed. Okay, so statement P represent switch S1 is closed. Statement P represents switch S1 is closed. So similarly for statement Q, okay, we have only two statement P and Q, and negation P, negation Q it is given, but they are the part of a P and Q. Okay, so we don't have to write it separately. Okay, switch S2 is closed at the statement P. Okay, switch S2 is closed. Okay, now negation of P represent switch S1 is closed or maybe it is on. Okay, okay, open. So switch S1 is closed or open. Switch S1 is closed or open, and negation Q it represent let me write this one again. Switch negation Q represent switch S2 is closed or open. Okay, switch S2 is closed or open. Okay, these are the logical representation of our statements. Okay, now convert our statement in the form of circuit. Okay, now see that we'll go for the plotting of our circuit. Here we do have space. Yes, now see that we have statement P and Q. P represent S1, so P represent S1, Q represent S2. Negation of P represent S1 dash, negation of Q represent S2 dash. Okay, replace all of the values in our statement. Now see that P and Q. Okay, that means switch P and the switch Q, between them we have AND. Okay, and sign represent series connection. Okay, and OR sign represent parallel connection. Okay, so take the P and Q, that means we have statement P, series start from here. Okay, so first statement here, series P and Q. Okay, so P and Q, that means between S1, P represent S1 here, Q represent S2 here. Okay, between them we have AND sign. Okay, that means they have series connection here. So again we have OR connection for what? Negation of P. Okay, that means for negation of P we have OR connection. Okay, now see that for OR connection we are taking is it is as series connection. Okay, so it starts from here. So negation of P means we have S1 dash. Yes, now next after that OR, again we have OR sign for this circuit. Okay, so OR sign means it goes to the downside. Okay, so completely negation of P or negation of P or and negation of Q. Okay, so it is the OR sign here between this one. So we'll go for this one like this. Okay, so negation of P or P and negation of Q. Okay, so P and negation of Q, we have two connection which is in the form of AND, that means these are the series connections. Okay, so consider these are the switches. Okay, yes, and between them we have S1 and Q, negation of Q means S2 dash. Okay, so this is our complete circuit. Okay, consider this one is a lamp. Okay, so I'm expecting that you all have understood how can we convert our logical expression in the form of switching circuit. Okay, so that's it we want in our board exam. So question asked for 4 marks in March 2017. Okay, nothing is difficult here. I'm expecting everything you all have understood. Even if you found anything difficult, let me know in comment section. Okay, I will come up with the same videos. Okay, let's go for the next question. Okay, we have next question. Simplify following circuit so that a new circuit has minimum number of switches. Also draw the simplified circuit. Okay, so first of all we have given switching circuit. Okay, using switching circuit we have to define it as the logical form. Okay, we have to define the logical form from our circuit. Okay, so it is similar like our previous example. I don't think so I have to explain this example. Okay, so you may try it for your homework. Okay, just define their switching table first. Okay, not a switching table, logical diagram first. Okay, so we have switching circuit here. Using that switching circuit, what do we do? Using the switching switching circuit, using the switching circuit we define as the symbolic form. Okay, we define symbolic form. Okay, first we define symbolic form and then subsequently we go for simplifying the circuit. Okay, so I'm expecting that that one is easier like a previous example. Okay, as I have solved in my previous example, you have to follow this one. Okay, why I'm giving it for your homework? Because this one is a time taking example and similar like my previous example. Okay, so we don't have to go for the repetition, that's why I given this example for your homework. So let me know and answer in my comment section. Okay, so if you found anything difficult, we'll go for that example in our next lecture. Okay, now let's move for the another example. Yes, construct the simplified circuit for the switching circuit. Okay, so similar like a previous one, draw the switching circuit first. Okay, switching circuit, so first of all you have to represent what is the S1, S2, S3, S1 dash, S2 dash, S3 dash. Okay, their negation, their statement. Okay, so we have statement S1, so we consider S1. Okay, the remaining part, okay, the written work you may do by yourself. Okay, like my previous example. So S1 can be represented as here switching circuit P. Okay, switch P as a switching circuit S1 closed. Okay, Q as a switching circuit S2 closed, R as a switching circuit S3 closed. Okay, so negation of P represents switching circuit S1 closed or maybe open. Okay, negation of q, switching circuit S2 close or maybe open, okay. And similarly for S3, okay. So that part you may do by yourself, or do it by yourself, okay. Now let's go for the writing. It's a symbolic form, okay. Now S1, directly write S1 as a P, okay. So that means P, after P we have series connection, okay. And for the series connection we take AND, not OR, we take AND, okay. So P AND, okay, for series connection we take P AND. Now see that between S2 and S3 we have parallel connection. So Q or R, okay. P and Q or R, this is the parallel connection between S2 and S3. Now after that we have again parallel connection between the statement and S2 dash, S2 dash, S3 dash, S2 dash and S1, okay. So it is a parallel connection, that means it goes as the OR, okay. S3 dash represent as a negation of R, okay. S2 dash, again between this we have AND, S2 dash represent negation of Q, and S1 represent and negation of S1, it is here P, okay. This is our symbolic form of our logical circuit, okay. So I'm expecting that you all have understood the symbolic form. The leftover part here to describe the switches you may do by yourself, okay. Like earlier I explained everything here, okay. So follow these steps and do this part by yourself, okay. I'm expecting you all have understood. Let's move for the next question. Question asked for 4 marks in October 2015 board exam, okay. Now construct the switching circuit for the following statement, okay. So we have to construct switching circuit using this statement, okay. Statement we have here P or negation of P and Q, or negation of Q and R, or negation of P, okay. So first of all define these switching circuits, okay. Switching circuits and their switches as a P, Q, R as a S1, S2, S3, and S1 is a negation of P, S2 it is a negation of Q, and S3 it is a negation of R, okay. Okay, so let's define P as a S1, okay. So remaining part you do by yourself, okay. So here S1 switch P as a switch S1 I consider here, okay. So that means switch S1 is a closed, okay. P as a switch S1, how the switch S1 is here closed, okay. Now next negation of a P is equal to S1 dash, okay, means closed or open, closed or, okay, switch closed or open, okay. Let me write it again. Closed or open, okay. And negation of P and negation of a Q, S2 dash, switch closed or open, okay. S2 dash, okay. After that Q switch S2, okay. Yes, now put all of them values in our statement and draw the circuit, okay. So now see that we have first P or negation of P and Q, okay. So P or means statement S1, okay. Draw the circuit S1 we have here, okay. Yes, between draw the circuit S1, okay. So we have OR connection for S1, go to the downside, and between OR P or we have a series connection first for the two statements, okay. This one is here, okay. Negation of P represent S1 dash, switch S1 dash, negation of, and Q represent R, okay. Sorry, Q represent S2. Yes, and between them we have OR connection, so it goes to the down as a parallel connection. Again we have negation of a Q and R, okay, or negation of P, okay. Again we have one circuit here which gives negation of Q or R, okay. Negation of Q, consider S2 dash, okay, and negation of Q and R, okay. Negation of Q and R, R is there, one more switching circuit remain, okay. Okay, negation of q and r, that means s2 dash, again negation of q and r, that means s2 here. Okay, PQR. Okay, Q represent, we have three statement. R we have to represent as here S3. Okay, switch S3. Okay, so negation of Q and S2 and S3. Okay, S2 and S3 having AND sign, and between of them we have or for negation of P. Okay, negation of P represent it as the S1 dash. Okay, this one is a S1 dash. Okay, this one, this circuit completed here, and complete circuit is having our lamp. Okay, this is the complete circuit from our logical statement. Now see that how easy it is to define the values. Okay, just need to think logically for finding their answers. Okay, I'm expecting that you all have understood. Question asked in March 2015 for 4 marks. Okay, so very easy question this one. Now let's go for the next. We have 2 more questions. Okay, so similarly like a previous example, you all have to define these examples. Okay, this question asks for 4 marks. Let me go for my slide. Yes. Now in my next example, we have to define similar like a switching circuit. Okay, switching circuit S1, S2 dash, S1 dash, S2 dash. Okay, this one is easier. Question asked in March 2014, 2017 for 4 marks. Okay, so S1 and S2 dash. Okay, now see that we have the S1, S2 dash, S1 dash and S2. Okay, so consider S1 P, S2 Q, S2 dash, negation of P, negation of Q, S2 dash comes as the negation of Q, and S1 dash negation of P. Okay, now represent all of this circuit in the form of a symbolic form, and after that you have to draw the switching circuit table. Okay, as we have done in our previous example. Follow this example similar like my previous one. So I will explain here to you all how can we define symbolic form only. Okay, so S1 we have P, between S2 dash and S1 we have parallel connection, so it goes to the OR. Okay, S2 dash represent negation of a Q. Okay, again we have S1 dash, S2 dash, all are having their connection with the series. Okay, it goes to the OR. S1 dash we represent it as the S1 dash we represent it as the negation of a P. After that S2 it is represent, and S2 we have here Q. Okay, this is our switch symbolic form of our switching circuit. Okay, so I'm expecting that you all have understood how can we define the switching circuit. Okay, so after that we have to construct switching table. Construct the switching table like 1 1 0 0 1 0 1 0 for the values. Okay, so P and Q. So leftover part I am expecting that you all have to do it by yourself. Okay, so do this next part by yourself. Okay, so last part we have similarly we have to do like a previous example. Okay, do it all of them by yourself. Okay, and let me know the solution for these questions. Okay, question asked in October 2013 for 4 marks. Okay, so I'm expecting that you all have understood everything from my today's lecture. Okay, even after if you found anything difficult, let me know in my comment section. I will come up with a similar video. Okay, so thank you everyone. Thank you for my today's lecture.